Um, Today I want to talk about, so you're stuck with me all day today, and then Sasha all day tomorrow. So I'm going to talk about exceptional collections and semi-orthogonal decompositions, which is about taking the derived category of some big variety and breaking it into simpler pieces, well, hopefully simpler pieces. So let's start with exceptional collections. So first, I'll write a title. Exceptional collections. So first, a definition. I'm going to try to use the Hagoromo chalk today instead of the great big white chalk. So if you can't see as well, feel free to complain, and I'll go back to the other one. An object E in, let's stay in the derived category of coherent sheaves today. You could talk about any triangulated category, but this is our favorite one, is exceptional if Hom from E to itself is one-dimensional, and Hom, well, X'd from E to E is 0 for I not equal to 0. So Hom is as small as can be, and then X1, X2, all of those things vanish. So in particular, it's simple, and because X1 vanishes, it's rigid, it doesn't deform. And it's sort of derived simple, if you like. Let's have some examples. So first of all, any line bundle on Pn. So Xt of O of t by itself. I can move this O of t over to the other side and have it be X from O to O of minus t. Right, I'll write this, even though it's, well, is X of O by O. That's the cohomology of O, which is, as you know, like that. And these will be some of our favorite exceptional objects. More generally, any line bundle on a Fano variety. So Fano means that the canonical bundle is, well, the dual of the canonical bundle is ample. So your favorite Fano varieties are maybe hypersurfaces in Pn of degree less than or equal to n. Right, so quadrics, cubic surfaces, cubics of dimension bigger than 2, quartics of dimension 3 or more. And how do you, so, but this is, so again, Xt of L by itself is Xt of O by itself is cohomology of O. And this is like this by Kodaira vanishing. So I guess I need to be in characteristic 0. If I want to appeal to Kodaira vanishing. So if you probably you don't remember the statement of Kodaira vanishing clearly enough to see this off the top of your head, but you can look it up. How shall we do this? If x tilde to x is the blow up at a point, So I have a point in X, and over it I have the exceptional divisor. And E, so E is the exceptional divisor, which is a Pn minus 1 if X is an n-dimensional variety. Have I got that right? No, it's a Pn minus 2. Nope. Let's see, if I blow up a point in a surface, this is a line, right? So it's n minus 1. Then OE, well, any line bundle on E is exceptional. For all T. So is exceptional as an, as an object of D of X tilde. So you have the blow up, and you're taking something that's just supported there on E. So let's show that. Let's just do it for T equals 0. So we have so here's a proof. You have an exact sequence, OX tilde of minus E goes to OX goes to OE. And we can take HOM from this to OE. OX tilde, thank you. We'll take HOM from this to OE. So we get 0 to HOM, OE, OE. To HOM from OX tilde to OE, it's just, well, this is going to be K, and then XI from OX tilde to OE is just HI of OE. So this is going to be K, 0, 0, and 0. So here I'm going to have X1 of OE with itself. So the interesting thing is I want to get a bunch of zeros here. Right, so this is what I need to justify for you. And to see that, so HOM, well, X'd from OX tilde to OE, or O of E to OE, minus E here. This is cohomology of OE of E. And maybe you remember the normal bundle, the exceptional bundle is O minus 1. Or the exceptional divisor is O minus 1. So this is 0. Questions about that? So your exceptional objects don't have to be vector bundles. They can be torsion sheaves. You could have many homogeneous vector bundles on homogeneous spaces, on Grassmannians, flag varieties. So for example, on the Grassmannian, you have this tautological subbundle and this tautological quotient bundle, and I won't prove it for you, but those are both exceptional. So maybe an exercise, the tangent bundle of Pn is exceptional. Actually, I didn't write this one in the handout, which I guess I haven't handed out yet. I didn't write that one in the handout because I just thought of it now. So maybe you can do that. Let's have some non-examples. If I take the skyscraper sheaf, O of a point, because x1 of OP with OP is just the tangent space. We've said this a few times. Eventually, we'll probably justify it, or maybe you already know. Anything that deforms is going to have some x1, and of course, a point can move. It's going to have some x1 with itself. Line bundles on, so we've seen a lot of line bundles here being exceptional, and we said on Fano varieties, line bundles are always exceptional. So let's take some varieties that are not Fano. So line bundles on curves of genus G bigger than 1, that are any curve that's not P1, right? Because X of LL is cohomology of O, as we've just seen, and this is 1 and G. So things of positively curved things of general type, tend not to have exceptional objects on them. And that's not, okay. I say tend not to. There are some varieties of general type with exceptional, where O is exceptional, but they're very rare. Another non-example, so if X is Calabi-Yau, so that means that the canonical bundle is OX. So for example, a K3 surface, a quintic threefold, those are two of your favorite Calabi-Yaus. Then X n of EE is by Serre duality Hom E tensor omega X dual. And omega X is trivial. So if E is not 0, then it has some non-zero map to it. It has the identity map to itself. So this is not 0 if E is not 0. So there are no exceptional objects on Calabi-Yaus. And for example, we saw yesterday that the cohomology of O of a K3 surface, well, a particular K3 surface, but it's true of all of them, looks like that. So instead, this is not an exceptional object, but what's called a spherical object, which are very interesting, but I don't think we'll have time to talk about them. Questions about the examples and non-examples? So next I want to talk about exceptional collections. Here it is. A collection of objects E1, E2, up to En in, well, you could be, again, you could be in any triangulated category, but this is my favorite one, is an exceptional collection if each EI is exceptional and there are no HOMs or exts from right to left. So our HOM from EI to EJ is 0 for all, whenever I is bigger than j. That right to left might seem silly, but once you see the examples, it'll become easy to remember. If you've heard of a strong exceptional collection, you can ask furthermore that from left to right there are HOMs but no higher exts. And that's a strong exceptional collection. But that won't come up today. So our favorite example is the Bailenson exceptional collection. So examples. So on Pn, you can take O of 1 up to O of n. Right, so you know X from O of I to O of j, this is the cohomology of O of j minus I. Right, so to go one step to the right, or one step to the left, you're talking about cohomology of O of 1, minus 1, O of minus 2, O of minus 3. And the longest one, the cohomology of O of minus n, vanishes. We couldn't have gone one more. Right, so the longest error is as long as we could have gone. If we put in O of n plus 1 here, then we would have X'd from O of n plus 1 to O. This is the cohomology of O minus n minus 1, which is the cohomology of the canonical bundle. And by Serre duality, that's dual of the cohomology of O, which is not 0. So this we can't include this. We can't go one step further. And of course, there are lots of HOMs from left to right, right? There are lots of sections of O of 1 and O of 2 and whatever. But no HOMs from right to left. And more generally, if X is Fano, we can write the canonical bundle is O of minus K for some unique ample O of 1. It's a theorem you can read maybe in Shafarevich's book, one of his books, that the Picard lattice of a Fano variety is discrete. In torsion, it's just z to the something. well, a Fano variety is simply connected, so the Picard lattice is just a free abelian group, and so omega x is ample, so it's a multiple, omega x is anti-ample, so it's a multiple of some unique smallest ample thing. This K is sometimes called the Fano index of the Fano manifold. And then, what do we want to say? Then O of 1 up to O of K minus 1 is an exceptional collection. And again, the proof is by Kodaira vanishing. So X from, let's just do the longest one. Well, X, I couldn't have gone one more, right? If I'd put O of K here, then I would have had an X from O of K back to O, because I would have had cohomology of O minus K. Well, let me write that. So I can't put O of K here, because X from O of K, O is cohomology of O minus K. It's not 0 by Serre duality, because O minus K is the canonical bundle. So X from, well, cohomology of O J minus I right, that's the thing we need to have vanish if J minus I, so we want this to be 0 if J minus I is less than what? Is less than K. And bigger than 0. So this is getting a little small. Is that what, before I explain why it's true, do you agree that that's what we want? We want no X from OI to OJ when I is bigger than J, but not that much bigger than J. Well, this is the cohomology of oh, I see. I want the negative ones. Thank you. If minus K is less than J minus I is less than 0. Thank you very much. So if I'm using Kodaira vanishing, again, I have to be in characteristic 0. But that's OK. There's a lot of action in characteristic 0. So Kodaira vanishing says that the positive cohomology, well, let me leave this as an exercise. To look up the statement of Kodaira vanishing and see that it kills that thing. On let's say X tilde is the blow up at a point of P2. We can take OE of minus 1, OX tilde, OX tilde of H, and OX tilde of 2H, where H is the pullback, right? So I have a map from here to P2, which I'm going to call F, and H is going to be pullback of the hyperplane class. So what do we need to see? We've seen that this is exceptional. That was okay. Well, we saw that OE was exceptional, but OE minus 1 is the same story. I need to see that these line bundles are exceptional. So the cohomology of OX tilde, this is the same as the cohomology of RF lower star. Well, let me call it R gamma. Is R gamma of RF lower star OX tilde. And something I want you to know about a blow-up is that the higher push forwards of O vanish. So this is R gamma of OX, of OP2, which is just K in degree 0. So these are exceptional. Xed, what next? Xed from O of H to O. So this is Xed from F upper star OP2 of 1 to F upper star, well, to OX tilde. And sorry, I go back and forth between X and R hom just to cohomology and R gamma, either to loosen you up or to irritate you. So this is, here I should put RF lower star OX tilde, and this is just OP2, as we said. There's no higher pushdowns. And this we already found to be 0. Right. So I guess the point is I took my exceptional collection downstairs, pulled it up, and it remained exceptional. And it was important that the push forward of O was O. And similarly, if I swap out this H for a 2H, then here I get a 2, and it's still okay. And then the interesting one will be to do Xed from O, well, let's call, well, OX tilde of any multiple of H to OE of minus 1. This is Xed from F upper star OP2 twisted by T, which is Xed from OP2 twisted by T to RF lower star OE of minus 1. So what can we say? I claim this is 0. And later, maybe in the next hour or the hour after, we'll see this in a more general context. But I think it's good to see it in the very down-to-earth setting. Right, we had E getting included into X tilde, mapping down via F to P2, and a point here. And if here I put OE minus 1 and include it and push down, that's the same as push down to this point and include. So already when I push that down, I'm just taking cohomology of OP1 of minus 1. Right, remember, pushing down to a point is the same as taking cohomology. And the cohomology of OP1 minus 1, 0. So to say it again, instead of taking the exceptional divisor, this line bundle and the exceptional divisor, and putting it here and worrying about F lower star, I could have gone this way around the square. Here it dies. And so we're done. You can imagine if I'd done the blow up of P3 at a point, then I would have gotten 3 line bundles from the base. And you can see now the exceptional divisor would be a P2. And there are 2 line bundles on P2 that vanish. So I could have stuck 2 things. I could have done here, I could have done OE minus 1 and OE minus 2. So the higher the codimension, the more things you get on the exceptional divisor that can fit in there. Also notice, if we blew up at 2 points, sorry, are there questions about that example before I go on? I can't tell whether you find this kind of calculation easy or hard. So if you find it easy, that's fine. If you find it hard, do ask. I promise if you have a question, someone else had the same question. Notice if maybe y was the blow up at 2 points of P2, and then we could do OE1 of minus 1, OE2 of minus 1, and then O of H, or O of H, O of 2H. And this will still be an exceptional collection. There are no HOMs between these, so no X's, because they have disjoint support. So again, there are no HOMs or X's from these to these by the calculation that we already did. But actually these exceptional, you would hope this would be true. There's no ordering on those points, so I could have put these exceptional objects in any order and still had an exceptional collection. Maybe this statement is a little mysterious. Why? I mean, you can see why having disjoint support should give you no HOMs between them, right? Because there's just no way for this stalk to map to that stalk. Right, so by the way, here's my picture of Y, and it has these 2 exceptional lines in it. And you could believe that there are no X's, but it's a little harder to see. Use the Grothendieck spectral sequence, the local global spectral sequence. So E2 is HP of X'd Q converging to X'd P plus Q. So because they have disjoint support, definitely there are no local X's. And then take cohomology. So these all vanish, and so when you take cohomology, they all vanish. So that all vanishes. That's probably the best. It's probably a better way to see it. Well, that's my exercise. It's not my. By the way, we say, I want to introduce this bit of notation early. So, yes? Uh-huh. Yes, absolutely. Yeah. So I'm going to blow up P2 at 2 distinct points. But I agree. If I blew up at one point and now I have this, and then I blew up a point there and now I have this, then there will almost surely be some X. You can see an X1 between those two. Yeah. Sorry, no, I'm thinking affinely. You might have to be careful about how you wouldn't expect to have no X there. So no, I want to blow up 2 points like that. Here's another definition. So given E and F in our favorite triangulated category, we write E is perpendicular to F to mean Rhom from E to F is 0. So the analogy is that taking Rhom is some kind of inner product, right? And you've seen that. So the analogy between Hom and an inner product you've seen before in adjoint functors, right? Hom from F, from some functor of E to F is Rhom from E to in this case, the right adjoint of F. When you talk about adjoint operators in analysis, there you really have a pairing. Here in categories we call them adjoints, just out of this metaphor. But you notice that saying that E perf F is it's not a symmetric relation in general, right? Like Serre duality would tell you instead E is orthogonal to F if and only if F is orthogonal to E tensor omega. Put that up there. Right. So if you're on a Calabi-Yau, I guess it is a symmetric relation. But we just said that today we don't really want to be on Calabi-Yaus. So you can see in an exceptional collection, these ones are orthogonal to those ones, but not the other way around. Right. On Pn, O minus 1 is perpendicular to O, but O is not perpendicular to O minus 1, to O of plus 1. Okay. Next, an exceptional collection is full I want to say that the smallest triangulated category containing all those objects is the whole thing. But we haven't talked about triangulated categories. So I'm going to say it this way. If you can generate every object of d of x from E1 up to En, by taking direct sums and shifts and cones. Right? If I have a map from this one to that one, then I can take the cone and get a new object. And So for every, I'm going to take this set of objects. Whenever there's a map between them, I'm going to take the cone of that and throw that in. And if I can get to any object of my category by doing that over and over and over, then we say that it generates the category. Oh yeah, finite direct sums. So the smallest subcategory that's closed under these three operations is the whole category. So here's a theorem of Beilinson. On Pn, O of 1 up to O, well, O of n is a full exceptional collection. By the way, when I say we can generate I mean every object is quasi-isomorphic to a thing that you get by, right? Not that it's literally in there, but it's quasi-isomorphic to something that you get this way. Because in this case, if I do these operations over and over and over again, taking cones between things that were cones between these things, I'm going to end up with a complex consisting only of sums of these n+1 line bundles. Right? I'm not going to, so in particular, every f in the derived category of Pn is quasi-isomorphic to a complex of whose terms are sums of those line bundles, those n+1 line bundles. Because if you remember how the cone works, it's you take this one plus a shift of that one, and then you put some funny differential on it. Yes. Oh, I see. You're worried that I might need a roof. Okay. Let's say it's actually you can do this, but you're right that it looks slightly stronger. So it's isomorphic in dx. Am I losing my mind? I'm just worried that when I take that roof and I play around with it, then I might jump out of this condition here. That, like all the cones that I would have to take. Yeah, no, so I'm having a. So it's true that every quasi-isomorphism is an isomorphism in the derived category, but you might worry about having a thing like that, and can you replace it with a quasi-isomorphism directly? Right. So if this one's a quasi-isomorphism and that one's a quasi-isomorphism, can we put something there that's a quasi-isomorphism? Right, but I'm saying that this quasi-isomorphism might not be invertible in the category of complexes, only formally invertible. Maybe we can come back. Maybe we can come back to this. But it's as good as a complex of those things. And so I want to prove this in not the way that Beilinson did. So proof is going to be first, we're going to generate all skyscraper sheaves. Right, so if I have O of a point that is cut out by a regular sequence of n linear forms, right, if my point is L1 is like that, then I can do this Koszul resolution. So the first step is going to come from O Pn of minus 1 to the n. Right, and it's going to be given by my n linear forms. And then the syzygies, well, the Koszul complex is going to come from n choose 2 things here, n choose 3 things, and finally at the end I'm going to have O minus n of n choose n things, which is 1. And so this point is generated by those things by taking a bunch of cones. Right? You take the first map, and you get the cone, and then you take the second map and you take the cone of that, and eventually you build up this complex. And so this thing is quasi-isomorphic to a point. So the subcategory generated by these n+1 objects contains all the points. Yes? That's actually a little bit harder. Sorry, how to get O of? Oh, I'm sorry. I switched which exceptional collection I was using. Let's twist this by n. Right. So now I have. Thank you very much. You go back and forth in your notes between whether you're using the positive line model. Right, so this becomes this. Here we have O of 1. And now we have O of n minus 2, O of n minus 1, O of n. And the point is that O of a point twisted by n is the same as O of a point. Yeah, thank you. There is an exercise to get on P2 to get O of 3 and O of minus 1 and this kind of thing out of this exceptional collection. But that's a different issue. Okay, so second, this implies that if I let this denote the subcategory generated by these things, let maybe C be the subcategory generated by O up to O of n, right? The subcategory, the full subcategory generated by closing under shifts and cones and finite direct sums. But of course, a finite direct sum is like a direct sum is just the cone on a zero morphism. So we don't need to say that over and over. So this thing here denotes the subcategory generated by them. And I want to talk about the let C perp be the set of all F in the big category such that E is perpendicular to F for all E in C, and perp C be the same thing on the other side. So then C perp and perp C, well, you don't actually have to do both of these. I just wanted to write them both down for you. And or perp C. It's, of course, nicer to write C perp, but it's a little bit nicer to work with perp C. So I'll prove that in a second. And third, is that because it's an exceptional collection, that implies that C is the whole category. So this third step, I definitely want to postpone until a later lecture. And it uses very strongly the fact that we have an exceptional collection. It's not true that if I take any random bunch of objects whose orthogonal is 0, then it generates the category. This condition, saying that the orthogonal is 0, is saying that those objects, it's called spanning the category. And if you generate, then you span, but if spanning is much weaker than generating in general. But for absolutely. Yes. So, and this is, as you say, if I take the subcategory generated by all structure sheaves of points, close it by taking cones, everything that I get is going to have 0-dimensional support. And yet I claim by this second step that I'm about to do that its orthogonal is 0. All right, so there's something, in this third step, there's something special about being an exceptional collection. So C contains all skyscraper sheaves, all of a point. And so the proposition that I want is for some F in the bounded derived category of coherent sheaves on X, if R-HOM from O of a point to F is 0 for all points, then F equals 0. And similarly, with R-HOM from F to all points. And it's important that we be in a bounded derived category here, because I'm going to make an inductive argument. Well, I'm going to use a spectral sequence, but there's going to be some inductive argument. So this will finish out the hour, I think, and then we'll come back to talking more about full exceptional collections. And this is expressed by saying points are a spanning class. So the proof we use spectral sequence E2PQ is going to go from RP Hom from O of the point to the qth cohomology sheaf of F. So I've been using H to mean sheaf cohomology for a long time, but now F is a complex, and I'm really just taking the cohomology of that complex. And this converges to R P plus Q Hom from O of a point to F. So if I put my P's this way, I better put P's this way, and my Q's that way. So I'm talking about X'd. And remember X'd, well, X'd P from O of a point to a sheaf is X'd N minus P from a sheaf to O of a point tensor omega. You could do this without using Serre duality all the time, but I prefer to do that. Right? So this will be 0 if my point is not in the support of my sheaf. But it will be non-zero if, let's see, if P is N and the point is in the support. Right, there's always Hom. You can always take your sheaf and map it to the skyscraper sheaf at a point that's right there. So I have some sheaf, and then I have the skyscraper sheaf at some point, which I'll do in another color. So I could do that skyscraper sheaf or that skyscraper sheaf. So here's the support. Right, so if this is out here, there are going to be no Homs, no X's. But if this is here, you're always going to have at least a Hom from your sheaf to the skyscraper sheaf. And so you're going to have an X'd N the other way, where N is the dimension of X. This spectral sequence is getting a little crowded. Let me put it over here. So let Q be maximal such that HQ of F is not 0, and let my point be in the support of HQ of F. Right, then in my spectral sequence, this way were my P's, and I'm going to have, P equals 0, P equals 1, up to P equals N. And here, this way are my Q's. Here's my maximal one. Then over here in the spectral sequence, I'm going to have xn of O of a point to HQ is not going to be 0. And what's going to happen, sorry, I'm going to run 1 more minute long. So this is an E2 page of and everything else is going to be contained down here. So this is the point where I'm using the fact that it's a bounded complex. It does have a last cohomology sheaf. Right, so up here, the cohomology sheaves are all 0, so there's nothing. And over here, there's also nothing because the dimension is too big. And so when I look at these boundary maps, these Ds in the spectral sequence, they're coming from 0 and going to 0, so they can't kill it. And then on the next page, so it survives to the 3rd page, where there are also no boundary maps that can kill it, and to the 4th page. And so it survives. So this term survives to the E infinity page. And it gives, and it gives some R n plus q hom from O of a point to F. So to run the whole thing contrapositively, if all these R homs were 0, then actually all the cohomology sheaves of F had to end up vanishing. Okay, I've already run long, so we'll see you. Oh, let me hand out the exercises. And if you have questions about this, we'll use this argument kind of a lot. So if you have questions about it, ask after the break. Maybe you can split that and send half of it back.